Alright guys, we're going to go ahead and start on the warm-up here for 9.5. So starting with number 1, again, if you've already worked through this, we can just kind of go with the video. If you haven't, you can pause it before I actually start going through all these. But anyway, here we go. Number 1, we're looking at for just identifying each transformation. And again, just as a quick reminder, the 3 types of things that you're going to be asked to do in terms of 9.5 is you're going to have to know how to identify a transformation, how to sketch a transformation, and how to label a transformation given points. So you'll see this warm-up, we're identifying. We're not actually having to draw, we just have to be able to tell what kind of transformation it is. And then we're labeling a transformation given points. So the only thing not on here is the actual sketches. So with this, number 1, what we're trying to go through is trying to see, first off, we have a translation. And if I look here, you kind of see how the points aren't exactly lining up. This is vertical and this one's not. It's at an angle. So that would not be a translation. You have a reflection, but you have to be able to see what kind of line it's rotating or reflecting over. But if I reflected it over a line, this piece would somehow be on top, and it's not. So by process elimination, you have to be able to see where the center of rotation is. But there is a rotation here. It's kind of turning this way. The point would probably be somewhere out here if you did the rotation. But it is a rotation. So again, you kind of figure that out by kind of seeing where the points are, and see I can't slide it because it turned, and if I reflected it, this point would be on top, and it's not. Okay, so process elimination, you can kind of figure that out. Number 2 is a little easier. You can see the line of reflection right there. Like if I took a point, if I was doing the sketch, and I reflected that point over, and I could do that with all my points, it's going to be congruent because I reflected over that line of reflection. You call that line L if you wanted. So here we got a rotation, and number 2, we have a reflection. Okay, so number 3, we're rotating ABC with the given vertices by the given angle. So with these, you got to remember your rotation rules. Now, again, I really say it. It's nice if you can memorize them. Great. If you can't, you can still draw them out. So again, I like to give you that reminder. But first off, if you have x comma y, and you're going to rotate 90 degrees, and this is in a counterclockwise direction, you are going to get negative yx. Okay. So again, you can draw that as well. And if you ever forget, and I would just kind of look at it this way, you have the xy plane, and you got a point here, x comma y. Okay, you're going to the right a lot and up a little. So if I reflect it 90 degrees, now you're going left a little, up a lot. So you see how that little guy was y, the big guy was x. So I'm going left a little, that's negative y, up a lot, that's positive x. So this would be negative y x. You can use that same rule if you were trying to go 180 degrees. So see how I made a line here between x, y, and then this point here? Well, here you see you're going left a lot, so that's negative x, and down a little, that's negative y. Well, that's your next rule. And just so you know, when I say these, I say negative, I mean technically it's opposite y, because if you started down here and then reflected, it would be your negative values would become positive. So it's opposite, which I'll show you as we go through these. But at 180 degrees, you have x comma y. Oops, x. I'll do that. X comma y, and you're going to go 180 degrees. In that case, it doesn't matter which direction you're going. You'll end up at the same point, but you're going to have negative x, negative y. Good study tip for you. I would write all the rules down for the coordinate plane, the xy plane translation rules in one spot, or just kind of make a highlight of them if they're easy to find in your notes. And make sure you kind of do a little quiz on them. You can do note cards or whatnot. But again, if you do happen to forget them, you can still sketch them and figure it out yourself. Okay, so number 3, rotate angle or triangle ABC with the given vertices by that given angle. So we're just going to use our rules here. We're going to go A prime. We're going to go B prime. And we're going to go C prime. Okay, so here we got the point 3, -4. So we're applying this rule up here. So we have 3 and that -4. So our x is 3, our y is -4. So when we flip the points around, this becomes opposite y. So since I already had a negative, I'm now going to have a +4, 3. So you flip the points, but the y value switches signs. Here we're going to flip the points, 1, 5 for B, but we're going to switch the y. So it's negative now. And then -4, 0 will now be 0, -4. But 0 isn't positive or negative, so you don't really have to change the sign, and there are your points. And if you know the rule, it's pretty quick. Okay, that's it. Honestly, there's really not much else to say. For B, I'll go ahead and change the color here. I got A prime. I have B prime and C prime. Now this one, all we're doing is we're switching the signs for the x and the y. So you see the x and the y are going to be the opposite sign. So it'll just be -1, 5, -7, that's a 7, -7, comma 1, and -3, -6. So if you know the rules, I mean, you can go through these ones really fast. Okay, so know those rules. And there we go, there's your warm-up. Alright, so with that, we're going to move into 9.5. 9.5 is our last unit in Chapter 9. And this is going to be on symmetry. So the lesson goal for today, students will be able to identify and describe symmetry in geometric figures. And we're actually going to do some 2D figures and some 3D ones. And again, you just need to be able to, the main thing is just, identify, know what type of figures are symmetric, and telling me how they're symmetric and how many lines of symmetry they have, things like that. So this hopefully isn't too bad. It's a little bit of visualization, being able to see these things. So let's kind of go into here. The big thing here, I mean, there is an example, just so you know, in the book that deals with, and in the notes, that deals with diatoms. So kind of got the statement up there. They're microscopic algae found in aquatic environments. This is just a very specific type of thing that we use symmetry on. But we need to know what symmetry is first, so I'm going to go ahead and circle this. This is something you may want to write down. Well, you need to write down. And again, it's understanding symmetry. So a figure has symmetry if there is a transformation of the figure such that the image coincides with the preimage. Now I can have plenty of examples as we go through, but just one super easy example is a rectangle. You can have a line of symmetry right here. And when they say there's a transformation so that the image coincides with the preimage, I could do a reflection. If I did a reflection, this would reflect onto itself because they're the same on both sides. And you can also do, in this case, a rotation. And those are the ones we'll typically do. I mean, we're not really going to talk about a translation to get it coinciding with itself. So the rotation, if I flipped it 180 degrees, it's going to be the same figure as well. Or it's going to coincide with itself. The vertices won't match if you labeled them, but the image itself would coincide with its preimage. So that's basically what symmetry is. If you can recognize symmetry, I mean, this is not the first time you've seen it. You should kind of know what symmetry is, hopefully, but if not, it's an fairly easy concept. Okay, so we're going to talk about line symmetry. I kind of drew a line on the rectangle on the previous page. So this is going to be called line symmetry. So a figure has line symmetry, or like I say, we call it reflection symmetry, if it can be reflected across a line so that the image coincides with the preimage. The line of symmetry, also called the axis of symmetry, divides a figure into two congruent halves. So that's what I had on the rectangle, and this one's a heart. You see how, again, there's the line of symmetry. It also can be a line of reflection, and if you reflected it over that line, it would be the same figure. Okay? Again, it's a very simple concept. Just know the words and understand what they're saying. Line of symmetry. That's what I'm talking about. Alright, so that being the concept, we just need to be able to find our own values for our own lines of symmetry. So here we're going to first tell whether each figure has a line of symmetry, and if so, we're going to copy the shape and draw all lines of symmetry. Now, I don't need to do that because I have the shapes, but you need to draw the shapes. So the first one's fairly easy to draw, so that's nice. So we're going to go ahead and draw a line of symmetry here if they have them. So looking at this first figure, what you want to do is see if there are any lines that I could reflect this over. Now remember I said, in this case lines, and it depends on how you look at this figure. If it looks like it's the same on the top as it is on the bottom, if it is, then you should be able to draw a line of symmetry right down the middle of that figure. So that would be a line of symmetry. Okay, now it does say, if it has line symmetry, copy the shape and draw all lines. Oops, I didn't mean to do that. You can copy all lines of symmetry. So there is another one here. If you can't see it, then well, I'll show you, but if you can go ahead and draw it. So the other one should be right here, going right down the middle vertically. So there's a couple lines, and again, there are going to be sometimes more than one line. Sometimes there's like 6, 7, 8 lines of symmetry. So don't be thinking that there's only one. It'll kind of limit you. All right, so that's A. You have 2 lines of symmetry. So you can say yes. I guess that would be a yes. Happy face because we got some. Okay. So B, you say, oh, I'll draw a line here. Well, no, that's not going to work on this one. It has to be the same on both sides. Here it's not. But if you draw one horizontally, you can get a line of symmetry. I'll do this as a solid line so we can see through the figure. Again, that's actually got to go like right in there. And if you reflected over that line, again, the figure would reflect onto itself. This is another yes. And again, I'm drawing how many there are. I mean, you can write that there's 2 here and 1 there if you want, but we can also see it. Okay. With C, we got this the flag. I'm gonna use my green here, so it's got red and blue already. So here we want to see, well, could I draw a vertical line? Well, no, I can't because it's not the same on the left and the right, but it is the same on top and bottom. So if you kind of decide to draw a line right down the middle, you would have a line of symmetry. You reflect it over that line, it'd be good. So that'd be another yes. Happy face. And you want to write 1, you can write 1. Okay. So again, that's just making sure you understand symmetry and you can find it in a figure. You just have to see it. But as long as you can see it, you should be fine. It's not too bad. Alright, so that's finding lines of symmetry. Rotational symmetry is the next type. And again, I talked about the 2 types of, when I did that rectangle, remember I talked about how you could do symmetry over reflections or rotations. So now we'll talk about the rotational symmetry. So it can be called radial symmetry. I'll usually use the word rotational. But the figure has rotational symmetry if it can be rotated about a point by an angle greater than 0 degrees. Because if it's 0 degrees, you haven't moved it. And less than 360. 360 is if I went in a complete circle, I'm back where I started. So it's somewhere in between. Okay, so that the image coincides with the pre-image. Alright, so this is just like I talked about with the rectangle again. Now we're using the rotations instead of the... Alright, so now, kind of giving an example of a rotational symmetry. We have a square. And a little tip here, this is only for squares actually, but not for squares, for what I call regular polygons. And let me kind of write that right away here. This is a regular polygon. And a regular polygon has it's going to have equal sides and angles. Some examples of some regular polygons are like an equilateral triangle. I can't draw this very well, but I'll do my best. Actually, I'll try to do like a hexagon. Yeah, it's really bad. But if they're all, that's really ugly. I'll try another one. Okay, so if we have regular hexagon, if it drew right, I'll just get the idea. Don't mind that part. So as long as the sides and angles are all the same, I guess it would be an equilateral triangle. All these angles would be the same as well. The Pentagon, actually the Pentagon building in Washington, is a regular pentagon as well. And a square is a regular polygon. So in this case, if you have that, each vertice, you can count the number of vertices, and you can get its rotational symmetry by dividing that by 360. So in this case, you'd go 360 divided by 4, and you're going to get 90 degrees. Now you can also see it. I mean, there's a little bit of just seeing this as well. So you kind of see if you rotated this 90 degrees, you know, it's going to kind of land, this point would land over here, that point would land over there, and so on. So that's kind of what we're trying to find, is we're trying to find, you know, the actual angle of the rotational symmetry. Now the order is how many rotational symmetries you can do in a circle. So this one would have 4, because that's how many rotational symmetries I would have. Now again, if you notice, that number matches this number, which is the number of vertices. Now again, that's only true again if we're dealing with regular polygons, but regular polygons are pretty common actually, so you might end up using that more often than not. Okay, so this is again the two things we're going to find with rotational symmetry: how much rotation do we need to map the figure onto itself, and then how many times can we do that within a 360-degree circle. Alright, so example 2, we're going to tell whether each figure has rotational symmetry. If it does, we're going to give the angle of rotational symmetry. So, and the order, how many of them there are. So to go ahead and get started here, we'll start here with this first figure. Now, this figure, I know it's got this little extra part on it, but this is a regular polygon. You'll see it has 3 points here, which means it's going to be, I should be able to rotate that point onto that point, this point onto this point, and this point onto this point, which means I should be able to do it 3 times. So what you would do is you'd go 360 divided by 3. I can actually do it out here. So 3 goes into 360 one time. Pull down my 6. 3 goes into 6 2 times. And because I'm going to pull down a 0, if 3 goes into 0 0 times, it'd be 120. So this is going to be 120 degrees for its rotational symmetry. So that's the rotational symmetry, and the order is again this number right here, which is 3. That's how many times it'll do it within a full circle. So that's A. Now with B, you have to kind of look and see, you know, this is not a regular polygon. See how the angles aren't the same and some of the sides are bigger, so I can't use that little trick on B. So you just got to look and see, you know, if I rotated this and I flipped the whole thing around, it would kind of end up on this point, and then if I did it over here, it would kind of get back to where I started. You can do that if you were talking about these 2 points as well. So this one, it does have rotational symmetry. And I forgot, I'll just put yes here, because you know it had rotational symmetry, and then I found the angle. So this one would be another yes. And again, some tricks here. I mean, you know it's only going to rotate if I kind of flip it halfway around in a full circle. Hopefully you can kind of see that, but if not, you can see that my order is 2. Because again, it's going to, there are kind of 2 points as I kind of went around here. I go here, and I'd rotate again, and I would have 2 for my order, which means you can just go 360 divided by 2, or 180 degrees, half of 360. Again, you can also see that I'm going halfway around the circle, so that'd be 180. Now this, for C, this is, we haven't had any no's yet, but this one's going to be a no, because this point, I want to see when it would coincide with another point here. This side's shorter, so it would basically be not there, not there. I don't have any points. As you can see, I'd have to go all the way around in a circle before I'd see it again, the same figure. So this would just be a big fat no. Little tear. You're sad. Okay. Like, I thought I was gonna, they'd all be yes, but no, it's not. Okay, so again, you're just kind of looking to see, you know, how could I rotate my figure so that it lies back on its same figure. And A and B, there are points where you could rotate them and they would, you know, land on at a point where the figure would look exactly the same. C, though, it does not. Okay, so remember, you got your order, you got your angle, and yes or no on those. All right. And this is some ones that there's some trickier figures, but you know, sometimes you're going to have line symmetry, sometimes you'll have rotational symmetry, sometimes you'll have both. So we're going to try to combine some of these. So like here it says describe the symmetry of each icon, copy each shape, and draw any lines of symmetry. So if you start there with the lines of symmetry, here you could try to draw the lines, but you see how it's kind of not the same on both sides because they have different colors. So this one, if you try to draw a line and you reflect it, the colors wouldn't match up. So this is going to be no line symmetry. But if I rotated it, again, we should be able to get these figures that kind of wrap around on each other. And it just depends on, you know, I'm thinking when I looked at it, I think the book likes to say that this is going to be rotational. It depends, I guess, on the colors, you know. If you want the colors to match, this would be no rotational symmetry. And if the colors don't matter, because again, actually in the line symmetry doesn't matter with the colors because it's not going to match anyway. If you see how it's got this little tail here, if I try to reflect it, there's no tail on this side, so it actually doesn't matter. It has no line symmetry. But the rotational symmetry, if the color doesn't matter, I guess you'd have rotational symmetry. I could rotate it 180 degrees, and this little piece here would kind of slide into here. So this whole piece would kind of slide in. Okay, it looks ugly, I know. All right, but this one, let's just say rotational. Rotational. If the colors don't matter, because I think the book says it does have rotational symmetry, but I like to be technical because, you know, if the colors matter, well, it doesn't. Because the figure itself would map on itself, but if you're looking at the actual pattern, you'd be able to tell that it's been rotated. All right, so next one, we got some line symmetry on this next one. If you look here, you could draw a line down here. So there's one. We could have a line here, which is 2. And I also could actually draw lines here for 3. And 4. So I have 4 lines of symmetry. So we have 4 lines of symmetry. And again, if we draw into rotational symmetry, think, you know, we kind of have 2 squares. So that's good. I mean, you can kind of look at either one because if you rotate, everything's going to rotate and it's all going to match anyway. So I have 4 points, which means I can do my rotational symmetry by going 360 over 4, which, by the way, that's 90 degrees. So we have a 90 degrees rotational symmetry. And if they wanted the order's 4. So again, anytime you got a regular polygon like a square, an equilateral triangle, regular pentagon, hexagon, or any other, like a star or any other type of figure, well, star isn't actually regular polygons, the angles aren't the same, but it is another example I'll show you in a minute, then you should be able to easily do that rotational symmetry by doing the division. So there's a little bit more examples. Oh, there's your diatoms. Okay, so example 3, describe the symmetry of each diatom. So that was the thing we kind of talked about on one of the first slides. Copy the shape and draw any lines of symmetry. If there's a rotational symmetry, give the angle and the order. Now with this one, I can't really see the figure, so I am going to, you know, I kind of can see it. It's just really hard. I don't know if you guys can. we kind of got these little guys shooting out here, so hopefully we can use that to help us. I'm going to go ahead and draw all those. Okay, so on this example, you want to try to see how many lines of symmetry it has. So I could do the rotational here in just a second, but if you try to do the line symmetry, I could probably rotate here, or reflect from that point. If I draw down the middle of those little triangles that form, and you can kind of see how these two pieces would match, those two pieces would match, and those two halves would match. Now you can kind of see you can do that for each little triangle. I can draw down the middle of that triangle, that triangle, that triangle, and that triangle. I don't want to get too messy here, so that's going to be 5 lines of symmetry. So I have my 5 lines of symmetry. And because, again, it's the same basic premise, I'm going to rotate this to the next triangle. So you kind of think of this as a point. You get your starting point, and it'll rotate here, there, there, and there. So I have 1, 2, 3, 4, 5 points that I can rotate it about. So you could treat this similarly to what we did with the regular polygons and go 360 divided by 5. If I do that work off to the side, 5 goes into 36 7 times, which is 35. Pull down my 0, and that would be 2. So this is going to be 72 degrees. So it's a 72 degree rotational symmetry. And the order in this case would be 5. It's a number we divided by. I know my writing's ugly. I get it. Okay, here, order. That's what I was supposed to write. I'm writing fast. Okay. So if you look over here, the next example, we got the same thing going on. We got all our points here. So again, I'm going to kind of look at all these points as they're coming out. It's hard to see in there, but this one's a little easier to see. Okay, so I'll draw one line of reflection just so you see it. I got this line of reflection going right through the middle. But again, this pattern repeats, so I would have, the same number of points will be the same number of lines of symmetry. So I have 1, 2, 3, 4, 5, 6, 7. So I have 7 lines of symmetry. That's 7's right there. Okay. And then the rotational symmetry is the same way, just like the last one. We're just going to go 360. Now, instead of divided by 5, divided by 7. So 7 goes into 36 5 times, which is 35. Pull this down. I get my 10. 7 goes into 10. That's going to be 1 time. And we're going to have a remainder on this. So that'd be a remainder of 3. So, oops. This is the same as 51 and 3/7 degrees. Now, because that's kind of a hard decimal, I would say, to memorize, you could probably go ahead and just get the decimal on that. That's fine. So 3 divided by 7 is about 0.428. So 0.43. So that's about 51.43 degrees. So this is going to have a 51.43 degree rotational symmetry. So the order is going to be 7. Alright, next up we got plane symmetry. Now this one's pretty quick. You have, instead of a line that cuts a figure into 2 congruent pieces, you're going to have a plane. So, plane symmetry divides the figure into 2 congruent halves. There we go. You can kind of see I can draw a plane. It cuts this figure in half. So this is just dealing with 3-dimensional figures. We also have symmetry about an axis. This is, again, type of rotational symmetry in a three-dimensional figure. So if you have a cylinder or any type of other figure, like if I had, you know, a prism, you can have a rotational symmetry there. Just, you know, if I rotated that triangle, there's 3 points, just like on that figure. You'd go 360 divided by 3, which is 120, and you would have a 120-degree rotational symmetry on that 3D figure. This cylinder has, you know, infinite number. I can rotate it any way I want, and it's going to look exactly the same. But again, that's kind of how these will work. So you got your rotational symmetry and your reflection, you know, your line symmetry with 3D figures. So, for example, like I said on here, tell whether each figure has plane symmetry, symmetry about an axis, or no symmetry. So like this one, you'd want to see, is there a plane that you can cut and divide this in half? So if I was trying to divide this cone in half, you know, you'd have to be able to find a plane that would cut through this figure. So if I'm trying to cut a plane in this figure this way, it's not going to work. As you can see, it's not the same on both sides. But if I drew a line down the middle, so I was kind of getting out of order there, I could do a rotational symmetry on this. So this is going to have no plane symmetry, but it does have rotational symmetry. Again, in that case, it would be actually infinite, because no matter how you rotate it, it's going to look the same. So this one, if you look here, if I try to draw my line down the middle here, this figure is kind of missing a hole in the pyramid. So this is going to have no rotational symmetry. And the same thing, if I try to draw a plane through that, it's not the same on top and bottom. So this has no symmetry at all. Okay, so basically, you know, you need to have something like a prism, technically a prism, to be able to get your plane symmetry. Both of these were not prisms, and a prism is something that it's got the same base on top and bottom. Like if I drew like a rectangular prism, then I could be able to draw a plane, kind of cutting that in half. It's hard to see. I'm terrible drawing those. That's why we don't have any plane symmetry here. It's kind of hard to draw them. But we had one, was it 2 slides before? You know, you can kind of see it that way. So that's a prism, and you can cut that in half. And then, you know, you can have planes, or not planes, you can have, you know, prisms that have rotational symmetry. That's fairly common. But also you can have them in pyramids. If this piece wasn't missing from the pyramid, this would have rotational symmetry. If it was a full pyramid, you would go 360 over 4, and it would be a 90-degree rotational symmetry, because you can see we'd have a square base, but you know, we didn't have that here, so we didn't have that symmetry. But that's what it would be if we did. Okay. All right, so we're gonna have our lesson quiz. Remember, you can pause this so you can get everything written down. So make sure you pause that video. It's just those 4 questions, so it should go pretty quick. And then assignments, again, don't worry, some of these are blank. We'll tell you what assignment you're doing, so don't worry about that. But what you do need to do is do your self-reflection. So make sure you get that reflection taken care of. Let us know what issues you may or may not have, and go ahead and get that lesson quiz done, and I'll see you in class.